A discussion on complex numbers starts with a discussion on iota, which is represented by I. Now iota or I equals under root of minus 1, right? So iota square is going to be minus 1. Iota cube is going to be minus 1 to the power 3, which is equal to minus 1 uh, under root squared into under root minus 1, which is equal to minus iota. Iota to the power 4 equals minus 1 under root iota, which is iota to the power 4, which is equal to minus 1 squared whole squared, which is equal to minus 1 squared, which is equal to 1, right? So to put simply, iota to the power 1 is iota itself, iota squared is minus 1, iota cube is minus iota, negative iota, and iota to the power 4 equals 1, right? Now if let's say we have iota to the power 5, it is going to be iota to the power 4 into iota, which gives us 1 into iota or iota itself, which means any any complex number of the form iota to the power 4n plus 1 will give us iota only, because all the powers of iota to the power 4 will become 1. Likewise, if iota carries a power 4n plus 2, right, then we are going to get minus 1. If iota's power is of the form 4n plus 3, then we are going to get minus iota, and if the power of iota is a multiple of 4, then we are going to get 1, right? So these are how the different powers of iota work. Now let's take an example. Let's say we have to solve iota to the power minus 7. So how do we solve this? Now iota to the power minus 7, based on the basic rules of indices, the negative power means 1 upon iota to the power 7, right? Which means this is equivalent to 1 upon iota to the power 4 multiplied by iota cube, and iota to the power 4 I know is 1. So essentially this thing now simplifies to 1 upon iota cube, right? But then we can't leave it like it is, right? So we multiply the numerator and the denominator by iota, right? So we get iota to the power 4 in the denominator, which will become 1, and iota in the numerator, so we get iota. So iota to the power minus 7 equals iota, right? So we are going to have to remove as many powers of 4, as many integral multiples of 4 in the power, because they'll become 1, and for denominator we'll just have to complete the power in the denominator to 4 again, and whatever we get in the numerator is going to be the answer, right? So this is how we can do all our computations on iota. Now from here I can derive another important result, and that result is that whenever we add any 4 consecutive powers of iota, they will end up looking like one of them will definitely be iota, the other one will be equal to minus 1, will be equal to minus I, and will be equal to 1, right? So if let's say I take any consecutive 4 powers of iota, let's say we have taken iota to the power 7 plus iota to the power 8 plus iota to the power 9 plus iota to the power 10. Now iota to the power 7, right, is going to be equal to iota to the power 4n plus 3, which is equal to minus iota, right? Iota to the power 8 is of the form iota to the power 4n, and we'll get 1 here. Iota to the power 9 is equivalent to this form 4n plus 1, so we get iota, and iota to the power 10 will be 4n plus 2 form, which will give us minus 1. Now when we add up the negative iota and the positive iota, they cancel each other. The plus 1 and the minus 1, they cancel each other, and we get 0, which gives us the result that if we add 4 successive powers of iota, we are going to get 0, right? So iota to the power, let's say p, plus iota to the power p plus 1 plus iota to the power p plus 2 plus iota to the power p plus 3 is always going to give us 0, right? So this is a result that we must keep in mind. Moving on. Now a complex number is a combination of real and imaginary, right? So a complex number will typically look like this, okay, where A is the real part of the complex number, right, and B, or rather IB, is the imaginary part of the complex number. Now clearly there's no way we can solve this to come up with a single answer, so we'll have to leave a complex number at A plus IB, right? So we have A, the real part, and IB, the imaginary part of this complex number. Now let's look at some of the properties of complex numbers. Complex numbers, first thing we should know is they are typically represented by the notation Z, right? So I could write Z as A plus IB as one of the complex numbers. Now let's say I have another complex number, let's call it Z dash, which is equal to C plus ID, then Z plus Z dash is just going to give me A plus C as the real part and I times B plus D as the imaginary part, right? So because I can do nothing, no addition is possible between the real part of this guy and the imaginary part of the other guy, right? So we'll just have to leave it like this. So sum of two complex numbers is equal to the sum of their real parts and the sum of their imaginary parts. Similarly, we can compute their difference. So Z minus Z dash is just going to be A minus C plus iota times B minus D, right? So this simply gives us the difference between two complex numbers. However, what happens when we multiply them? Now when we multiply them, then this whole thing multiplies with this whole thing and we get A plus IB multiplied by C plus ID, and using the rules of multiplication, and when we open these brackets we get AC plus I times AD, right? So A multiplied by C, A multiplied by ID, plus I times BC plus, now notice that IB into ID will give us I square, right, into BD. Right, so when we solve, we notice that Z dash equals AC minus BD as the real part. Now why is this happened? Because I square becomes -1, right, and BD, it becomes negative BD because it is multiplied by I square, right, and we get iota times AD plus BC, right? So the complex number which we get as a result of product of two complex numbers is real into real minus imaginary into imaginary, right? This becomes the real part, plus iota times real into imaginary plus imaginary into real, right? So this is how we compute the product of two complex numbers. Now if, let's say, if you were to tell me that Z and Z dash are equal, then the only way they will be equal is if the real part equals the real part and the imaginary part equals the imaginary part. That is the only way for two complex numbers to be equal, right? Next let's move on to the conjugates of complex numbers. Now conjugate of a complex number, let's say A plus IB, which is Z, the conjugate, first thing we should know, is represented by Z bar, right? So a bar on top of the complex number, or even a bar on the expanded complex number implies that we are talking about its conjugate, and conjugate is simply you keep the real part intact, you only negate the complex part or the imaginary part, right? So essentially z bar in this case is going to be equal to a minus ib, right? So the conjugates, the conjugate of a plus ib being a minus ib, and the conjugate of the conjugate is going to be a minus negative ib, and we are going to get a plus ib, right? So this gives us the first property, that the conjugate of the conjugate is the original complex number itself, right? So let's look at some of the other properties of conjugates, right? So this is the first property that we've just done. Conjugate of a conjugate is the original complex number itself. The next property is going to be that if you tell me that a complex number is equal to its conjugate, right, then the only way this is possible is if its imaginary part does not exist, right? That means a plus ib and a minus ib are equal, which means that b equals 0, right? So this is a purely real complex number, right? However, if you tell me that a complex number is equal to the negative of its conjugate, then clearly a and minus a, right, they are going to be equal, which means that a equals 0, which means that this complex number is purely imaginary, right? So in this case b is 0, in this case a is 0, right? Moving on, the next property is that the real part of a complex number, right, or even the real part of its conjugate is given by the sum of the complex number and its conjugate and divided by 2. Now why? Because you have a plus ib here and you have a minus ib here, right? So when you add up a plus ib and a minus ib, you get 2a. Now you divide it by 2 to get a, right? That's the next property. And the property which follows this, right, is that the imaginary part of the complex number is just simply the difference between the complex number and its conjugate divided by 2, exactly like what we've done for the real part above. What you also got to do is you got to eliminate the iota, right? So you just divide it by iota as well. Moving on, the conjugate of sum of two complex numbers is going to be the sum of their conjugates, right? So it doesn't matter whether you add them up and then take the conjugate, or you separately take their conjugates and then add them up, you're going to end up with the same complex number, right? Similarly for the negative side, right? So if you subtract two complex numbers and you find its conjugate, it's going to be exactly same as subtracting their respective conjugates. Then if you multiply two complex numbers, right, and you take the conjugate of the product, it is going to be equal to their respective conjugates, right, and their product, right? So either you multiply them and you take the conjugate of the result, or you take their individual conjugates and you multiply, you'll still get the same result. And the same goes for division, right? So you divide two complex numbers and you take their conjugate is going to be the same as you take their conjugates and you divide them, right? Then the next property is that if, let's say, you have two complex numbers, right, z1 and z2, right? If you multiply z1 with the conjugate of z2 and you add that to the conjugate of z1 multiplied by z2, you're going to get 2 times the real part of z1 conjugate z2, right? And this is also going to be equal to twice the real part of z1 multiplied by the conjugate of z2, right? Then moving on, z, a complex number to the power n, right? If you have to take its conjugate, it's going to be equal to the conjugate of this complex number to the power n. And actually, if you notice, this 10th property can be derived from this 7th property itself, right? So hopefully the properties of conjugates are clear. We're going to have to use these properties in certain computations regarding complex numbers. Now let's move on to the next concept, and that is modulus of a complex number. Now modulus of a complex number is represented by the mod, the bars around the complex number, right? So this is same as if let's say the complex number were equal to a plus ib, right? Then the mod will be represented by this, and the mod computation is actually equal to the under root of the square of the real part plus the square of the imaginary part, right? So this is the modulus of a complex number. Now what are the properties of complex number? The first thing is, if the complex number is not equal to 0 plus 0i, right, then the mod is always going to be positive, right? Because essentially what you're doing is you're squaring it up and then taking the positive root, then the modulus is always going to be greater than 0, right? Then the next property is that for a complex number z, right, the modulus of this complex number is going to be the same as the modulus of its conjugate, because this is a plus ib, so this is going to be equal to a square plus b square under root. Now this is a minus ib, this is just simply going to be a square plus the square of negative b under root, right, which gives us essentially the same result, so it doesn't matter. Then the next property is that the product of a complex number and its conjugate, right, will give us the square of the modulus. Now why does this happen? Because if let's say the complex number were a plus ib, right, so I'm basically, what I'm doing is I'm multiplying a plus ib with a minus ib, right? Now this is equivalent to a square minus the square of ib, right? This gives us a square plus b square, because I square becomes minus 1 itself, right? And the modulus of z is under root of a square plus b square, right? You square it, you get this, which is equal to the square of the mod, right? Now the next property of complex numbers is that if let's say you have two complex numbers, z1 and z2, right, then if you add them, right, and you take the modulus of their sum, right, this is going to be less than or equal to their individual moduli added, right? Now this holds true even for the subtraction, right? So if there's two complex numbers that you add, you take the modulus of the summation, right, it is going to be less than or equal to their individual moduli added, right? Now you could generalize this also to, let's say, n number of complex numbers, right, up to zn. Now this is going to be less than or equal to their individual moduli added plus zn, right? Then the product of two moduli, right, let's say you multiply two complex numbers, these two complex numbers, and you take the modulus of their product, this is going to be equal to their individual moduli multiplied. Right, so you take z1 and z2, you multiply them, you take the modulus of the resultant complex number. You take the modulus of z1, you take the modulus of z2, you multiply them with each other, you get the same result. The same thing holds for division. If let's say you got two complex numbers, you divide one by the other, then this is going to be equal to the modulus of z1 divided by the modulus of z2, right? Then we can use this to give us the seventh property, and that is, if you take the modulus of a complex number computed by taking the nth power of one complex number, then this is going to be equal to the complex number's modulus to the power n, right? So hope these properties are clear.